we're gonna have two different kind of stability to talk about. One we talk about and leave it, and one we talk about and take it from here. And I'm hoping I can finish that today. What time is it? About 15 minutes we have? Okay, 10 minutes. Now we have stability. I have static stability, and I have dynamic stability. For static stability, case number 1, and for here, case number 2. I can have 3 situations or 3 subjects. The load distribution is gonna make a difference. How the load is distributed, because the load, different distribution of the load can cause moment, can cause torsion, can cause whatever. By changing the stress distribution, you are changing the whole situation. So when we are looking at the load distribution, we can look at static and or steady steady state system of aerodynamic and elasticity loading. As we said, by definition, that's what aeroelasticity is. We have a combination of, we have a marriage between the aerodynamics and the structure. He put the structure into the wind tunnel. So that's the combination of. So the load distribution in this can cause 2 situations. And that will be based on, as I mentioned earlier, how stiff is the structure, how flexible is the structure. If the structure is very flexible or the structure is sufficiently, that can lead to either we have here divergence the C. Divergence, and that will lead to failure. All right. For the case of extremely flexible aircraft or spacecraft structure. So for the case of extremely flexible situation, those sets of loads from aerodynamics and structure can lead to failure. If it's sufficiently flexible, not extremely, then we can reach, and let me erase this so I can have room if the pen allow me. We can reach the third situation, which is central reversal. Please don't do this to me. Why are you doing this to me? I don't know. what did I write? All right. This case, control reverse. Meaning what? So we have the load applied to the aircraft or spacecraft structure. In the case of extremely flexible situation, this load will cause divergence. The divergence can cause me to fail or to fracture. Or if it is sufficiently flexible, then it will, instead of going to diverge, it will converge and kind of like reach some kind of stability. So this will be stable. And statically stable. So on the static situation, which is again, that's not our subject, but just is all coming from stiffness. So for the stiffness, we have a situation where static stability can either lead to failure if the structure is extremely flexible, or lead to stability, will converge to stability instead of diverge and go out of business and fail, and if it's sufficiently flexible. Those here are related to the static stability, and that's not my subject. But it is an element, or it's a part of the stiffness problem. So where is my subject? When I get to the dynamic stability. Then for dynamic stability, when do I have dynamic? Is when I have dynamic loading right here, which is coming from the inertia of the structure. So not just the aerodynamic forces and the structure forces, but adding to it, to the inertia structure forces, that's a dynamic loading, and that can cause the dynamic situation. And so now, when we are talking about dynamic, stability, that's when, come on. We have also the three situation, and one of them is our subject for maybe a week or so from here, or till the end of next week. And that's the one we like to talk about, the flutter, right? Or here, the buffeting, and in here, come back, dynamic response. And really, this here is our subject, and this is the most important subject, which is under the structure vibration. What do we mean, or what that means? And the time, I have 3 minutes. I will just give you one definition and I will stop. All right, and that's what we need. So this one here is an important element of the dynamic problem of aero, come on, of aeroelasticity, period. And flutter, please, is defined as the dynamic instability of an elastic body in an air stream, as I said, like a wind tunnel, and is produced by aerodynamic forces which results from the deflection of the elastic body from its undeformed state, right? And the determination of critical or flutter speed for the continuous structure of aircraft or spacecraft is unfortunately a complex process, since such structure possess an infinity number of natural or normal modes of vibrations. So it's not easy. But that's the subject we're gonna challenge starting on Thursday, is how to calculate those natural frequencies for a given structure. I'm out of time. I'm sorry I kept you late. Any question before we quit for this lecture? So we talked 1 hour today about stability, buckling, and now we're talking about dynamic stability in the aeroelasticity, which will be the last topic I need to talk about as far as failure analysis. And we will see, my goal is to finish a little bit talking about the what we're gonna do early on Thursday for 10-15 minutes, and then I start doing some problem, at least 2 or 3. Any questions? If there is no question, sorry that I kept you, I think, 4 minutes. Please forgive me. Thank you very much for your attendance and listening, and good luck studying for the quiz on Thursday. And remember, I have office hours tomorrow from 1 to 5 on the same link. Good luck. Stay well, stay healthy, and take care. And thank you, everyone. Bye-bye.
Thank you.
You are more than welcome. Thank you.
Dr. K.
Yes, sir.
In the notes, when you were talking about the monotonic loading, and you had the stress strain graph, and it went into the negative. Is the negative side of it the compression?
Yes. Yes. So you talk about the fatigue curve.
Yeah, the fatigue curve.
So you load it in tension, and then you unload the tension. Then you load it in compression, and then you unload it in compression.
Okay. Compression is negative.
Yeah. And I forgot to say, but well, as I said, we're not talking fatigue and fractional mechanics. The material has two sigma yields. Every material. People for a long time they thought that sigma yield in tension and sigma yield in compression are equal, but till a gentleman came by name Baumschinger. So Mr. Baumschinger said that the sigma yield in tension is a little bit bigger than sigma yield in compression. So for you and I in 331, 431, homogeneous isotropic material, okay. But when you really get to the fracture mechanics analysis, we insist on that sigma yield is different from in tension is different from compression. And when we get to composite, like when we did theory of failure for this class, we were worrying only about sigma yield, right? And that's because the material has only one sigma yield. When you deal with composite, you have to say there is sigma yield in tension, there is sigma yield in compression, and also there is shear for fibers, and there is sigma yield in tension, sigma yield in compression, and shear for the matrix. So, but the shear is the same. So you are dealing really with 5 material strength: sigma yield in tension for fiber and matrix, sigma yield in compression for fiber and the matrix, and the shear for both of them, which is equal. So yes, when you go below the curve, that's the compression. Yes.
Okay, and you said that the tension yield is a little bit higher than the compression yield.
Baumschinger. Yes, but we don't say that here. But really, when you get to composite, you insist on it. And when you get to fracture mechanics and studying fatigue, because now we are serious about worrying about fracturing, yes, we insist that sigma yield in tension is bigger than sigma yield. They are not equal, but sigma yield in tension is higher, bigger than sigma yield in compression. And that's true for all the material. Yes.
All right, thank you.
Oh, you are more than welcome. I see somebody here with the chat saying, who gonna tell him that it's 6? Well, you guys need to tell me, because I don't look at the watch all the time. So feel free to stop me when it's a time. And as I said, I'm sorry I kept you for 4 minutes extra. So and then somebody said that I think he is gonna stop after the definition, which is true, maybe. All right. Any other questions? All right. Mm. I have only 18, and it's 6:10. Can everybody hear me?
Yes.
And can everybody see the screen?
Yes.
All right, thank you. All right. And today is like what we did with the section 1. I am hoping that we will be done with the stability, the second topic of failure. And I think, remind me, or somebody can remind me, because as I mentioned, my feeling that we were ahead of the section number 1. So did we finish the problem, which is a built-in on both sides? The problem we are doing, we're still doing failure, analysis, and design for safety. That's our topic we've been talking about. Failure analysis and design for safety. And we already talked about 2 kind of them, statics. Come on, statics. And under that, we talk about yielding, and that's tension. And we talk about buckling, or really I should say instability, and that was compression. We are done with this completely. We are trying to finish this one today. And then if we can today, we're gonna talk about the dynamic one. Dynamic. And in the dynamic one, we will be talking about really the vibration, which we start talking about it, or at least introducing it in the other class. In the other class, it took me an hour to cover or to finish the buckling instability, and then an hour talking about the third type of failure, which is vibration. So I am not quite sure. I think we already done with this problem. Please let me know. I think we are done with this problem. And this problem, if I'm not mistaken, we did it in this class, EI, come on, EI is constant, EI. We did, and let me know if we did, that delta y is a 1 minus cosine 2 pi x over L. And we did, if I'm not mistaken, with you in this class, we assumed y to be a plus bx plus cx squared plus dx cubed plus fx to the 4. And we said this one here give us an answer of, p equal 4 pi square EI over L square. And we said this one here give me P to be 4. I don't know why this page, maybe I should look for another page. B equal 4.26 pi square EI over L square. Are we done with this or not yet? Can somebody tell me? I'm sorry?
Yeah, we already covered that.
Okay. Any question about these two problems? And as we said, when we assume the difference between these two problems is what? We assume delta y, and we assume 1 minus cosine. In here, we assume y, and we assume polynomial function. You can do the same problem by assuming delta y or assuming y. And you can assume a cosine, a trig function, or you can assume polynomial function. Assuming delta y or y is not going to make a difference. What's going to make a difference is the function you assume. And as you can see, we said last time, the assuming the trig is more accurate than the polynomial. So this answer here, 4, the answer here is 4.26. The 4 is the exact solution. So this answer for the second problem was not as good as the first one. If we need to do this, get this to be as good as this, we need to add more terms. But the concept is clear. The concept is I can use delta y or y. I can use a trig function or polynomial function. And also, if we use delta y, then we calculate delta u and delta v. If we assume y, then we calculate u and we calculate v. And first minimum principle. Could be delta U plus delta V equals 0. Or delta U equal minus delta V. In here, partial U plus V, partial Q, partial Q equals 0. Or partial Q, come on, right. Or partial U, partial Q, plus partial V, partial Q equals 0. Or partial U, partial Q, partial U, partial Q minus equal minus partial V, partial Q. Any one of those is first minimum principle. Any one of those is first minimum principle. We use this with delta Y. We use this with assuming Y. Any question about these two problems? If there is no question, and I don't know if I think I told you that we're gonna do this today, and I asked you to do it, but then I said, I didn't think you will. Anybody try to do the next problem? And I understand you received yesterday, I told Martin and Dylan to send you the email yesterday. Did you get the email with the homework? Did you receive the homework for the stability problem, for these problems?
I didn't.
I didn't get an email about that.
Oh, you didn't get the homework yet?
I didn't get it either. I don't think they sent it out.
All right, I will make sure that.
Dylan's actually in the chat right now.
I'm sorry, say again?
It looks like Dylan's in the chat right now. So we can
Yeah,
join him directly.
he said he will be attending this class because of the vibration. I didn't cover that last year. But okay, I will make sure with Dylan and Martin that but anyway, the homework, it's the, I think there are 3 problems, and I already did them in the class here. As a matter of fact, I'm doing one of them right now. And each one of those 3 problems you have in the homework, I work it out with you in the class, and I work it out with you in a different or multiple way, by assuming Y, or by assuming delta Y, or assuming a trig function, or assuming a polynomial function. So I'm gonna do this problem here. I'm gonna do it again both using the trig function with delta Y, and using a trig function with Y. So the last 2 problems I'm gonna do today, or for this subject, is I think this is number 5 and 6, if I'm not mistaken. Okay. So this is the problem, which is again one of the homework problem. Different boundary condition. And so it's gonna do like this, it's gonna do like that. I'm sorry, I ordered a new pen, but it didn't arrive, so I'm a little bit in trouble. So here is Y, here is X, here is L, and here is I is variable. Function of X is I0, 1 minus 3 X over L. So now you know these are the homework problem anyway. All right, so 1 minus 1 minus 3, and this is 1 minus 3. So it's 1 minus 3. Ah, gosh, please. 1 minus 3. Okay. So again, the first one, we're going to say delta Y is A cosine pi x over L. So we assuming a trig function for delta y. And since we got the delta y, before we go anywhere, let's get what? Delta y dash and delta y double dash. Double dash. Delta y dash will be minus a pi over L. I need to over L sine pi x over L, and here it will be minus a pi square. You think if I get another page will be better? What is the answer?
I
Can
like
you help me?
the sound of that. I think opening a new page maybe in the notebook or restarting it.
Yeah, let me see. Give me a second, everyone. No, it's the page is giving me a hard time. Let me. Just let me make sure to. Can you see what I'm writing?
Uh-huh.
Yes or no?
Yes. Yes. Yes.
See what I'm writing. Okay. Let's see if this is better. So we were saying that delta y is we got it. And did I write delta y prime and delta y double prime?
You're in the process of writing delta y double prime.
Okay. So delta y prime, I will rewrite it. And I will write delta y prime is minus a pi, still doing the same thing, pi over L.
Did you close the previous page?
I think I did, right? Let me check. I think I did.
This might be worth restarting.
Okay. I'm sorry, say again?
This might be worth restarting the OneNote.
Let me start doing it. Not even. Quick notes. New section, I add a page. Tilted page.
Yeah, that looks good.
Is better? At least we can try it, right?
Right.
Can you see this?
Yes.
Yep.
All right. All right. We'll try. We'll see. I'm sorry. And also my pen is really not doing well. So we are saying delta y is equal, for the third time, minus a, it's not working, minus a pi over L sine pi x over L, and delta y double prime, that's prime, is minus a pi over L square and cosine pi x over L. So we got delta y prime and delta y double prime. Now, since we got these two, this will give me delta V, and this should give me delta U. So delta U is what? 2. I'm gonna go use symmetry, so I'm gonna go from 0 to L over 2, and I'm gonna say EI over 2, and as we did before, delta Y double prime square, because Y square is 0 and the other one is cancel. So dx, and that gives me delta U when we integrate, because we're gonna put this here, comes to be 3 e pi to the 4 I0 over 16 L cube times 1 minus 2 over I square and times A square. Equation 1. So I got here A into the second order. And then same way, move this up, I get the
Dr.
delta
K.
V. Yes, ma'am.
Why did you only integrate to L over 2?
Just it's easier. I took advantage of the symmetry.
Oh, okay. Thank you.
Because for this problem, the axis is in the middle. They are not from the top.
Why can we
Makes
make
sense?
why can we use symmetry if our I is not constant?
Oh, the fact that I is not constant, that means I stays inside the integration.
Right. Okay. Thank you.
That's all. Yes, you're welcome. So delta V will be the same idea. What is the equation for delta V? Delta V is minus 2 P over 2 integration from 0 to L over 2 delta Y prime square dx. And I have delta Y prime, we already wrote it 3 times. So that will give me delta V will be minus pi square P over 4L times A square. That's equation 2. What is the good news, everyone? That A square is A square. That means when I come to talk about delta U plus delta V equals 0, they cancel. Delta U plus delta V equals 0, or delta U is minus delta V. Either way is first minimum principle. And that gives me P, which will be P critical, which will be P Euler, will be what? 8.902 EI 0 over L square. If I want it to look like what you and I know has pi square in it, well, then P will be 0.902 pi square EI 0 over L square. Any question? The only difference between the two answers, one of them, it doesn't have pi square, so this term here together is equal to this term. Any questions? Okay, same problem, same everything. Just now I'm gonna do trig. which is like before, but now I'm gonna assume y, and I'm gonna make it 2 terms instead of 1 term. So what do we expect the accuracy be, better or worse? Any input?
Could you repeat the question, Dr. K?
The question is, we are doing the same problem. What we did, we just finished, we came up with this answer. We assume delta y and only 1 trig term, a cosine, right? Now I am gonna do this same problem, but I'm gonna say y equal a cosine pi x over L and b cosine 3 pi x over L. My question, do you expect this answer, this is gonna give me a better answer than the one before or the other way around?
This one?
This one, yes? So you're right. The idea, it doesn't matter if you assume delta y or y. What matters is the function itself. The first one, I assume delta y. I'm assuming here y, it doesn't matter. But this one will be better because what? I have 2 terms. This is very much like this. Summation beta n cosine n pi x over L for n is odd. This is the same equation where n for even is equal 0, because it's gonna go like this. So here is the thing here, but we are gonna like have like something like, something like that. So when we are even, the deflection will be 0. So this here should give me a better answer. The reason because I have 2 terms. Let's see if that's gonna be the case. And since I assume the y, then I'm gonna calculate the u and the v. Where I assume the delta y, I calculate the delta u and the delta v. Whereas delta u is u after minus u before, and delta v is v after minus v before. So in this case, we're gonna say what? If this is y, so here is y prime, will be what? Minus a pi over L, and then I have sine pi x over L, then I have minus b, come on, y equal minus a pi over L sine pi x over L minus p 3 pi over L sine 3 pi x over L. And y double prime, that's prime, double prime will be minus a pi square over L square cosine pi x over L minus p 9 pi square over L square cosine 3 pi x over L. Right? So I got the y, I got the y prime, I got the y prime. This is gonna give me the v, this is gonna give me the u. So what is u? Will be, come on, what is the u? Is 2, and then the E out. I'm gonna leave the I in, 0 to L over 2. And then I have the I. And then I have what? The y double prime is square. And I have the dx. And the I stays inside the integration. And then I will do the partial u, partial a, and will be what? The 2, the e, the integration from 0 to L over 2. Then what? I, and then y double prime, then partial y double prime, partial a, dx, and partial u, partial b will be the same, 2e from 0 to L over 2. Here is the I, here is the y double prime, and here is the partial y double prime, partial b dx.
Dr.
So
K,
really, yes, sir.
for the y double prime, I think it cut out when you were finishing the coefficient for the b. Should that include a cosine of 3 pi x over L?
For y double prime?
Yeah, because you have b
Oh,
times
yeah.
9 pi
I didn't
squared
write
over
that.
L.
Oh, I'm sorry. Thank you, sir. Did it go away?
Yeah, I think it cut out as you were doing it.
This is better?
Awesome, thank you.
Yes, sir. Thank you for telling me. I didn't see it. Yeah, thank you. I appreciate that. Then we got partial u, partial a, partial u, partial p. The same for the v, but let's finish this. So really what this will give me here, I get two equations. Partial u, partial a will be, here is the final answer, 4ei0 L cube A plus 50 EI0 over L cube and B. And partial U, partial B will be, where are you? Right here, is 50 EI0 over L cube A and 3,100, if I didn't make a mistake, EI0 over L cube B. So those are the two equations. You notice, and somebody asked me in the other class, somebody said, why we didn't use the boundary condition to find A and B? Number one, the axes are in the center. Second, I want to show you that I don't have to use boundary condition. All what I have to do is do Rayleigh-Ridge twice. I have two unknowns, A and B. So partial U, partial A, and partial U, partial B, two equations, two unknowns. And guess what? Even if you have two unknowns, the good news that they will cancel. The power of A and the power of B coming from partial U and partial V will be equal. And then the A and B will be eliminated. And again, I will end up with one equation, one unknown, and that will be the B critical. So just kind of showing you that, as we said, we use the approximate method when there is no exact method and or when it's hard. And also we find the constant by using boundary condition, but sometimes we don't have the boundary condition, or sometimes we don't have enough boundary condition. So in this case, I did not use the boundary condition. I used Rayleigh-Ridge twice, one time for A and one time for B. So the same way, I can come up with the V to be minus or minus P over 2 times 2, because I'm integrating from 0 to L over 2. and y prime square and dx. So again, if I do partial v, partial a, I will get what? Minus 2p from 0 to L over 2 y prime, partial a dx, which that will give me minus 4.92 p over L again times a, and partial v, partial b, the same idea, will be minus 2p 0 to L over 2 y prime, partial b dx will be minus 44.3 p over L times b. So I have here, can everybody see I have two equations here and here? So I can add them together and say what? Partial u, partial a, plus partial v, partial a equals 0, and partial u, partial b, plus partial v, partial b equals 0. 1, 2 equations. So let's do that. So we have a times 44 ei0 over L square minus 4.92 p. This is the A. And the B. And what? 50 the ei0 over L square over that equals 0. And the other equation is A, 50 ei0 over L square plus B, 3,100 ei0 over L square minus 44.3 B equals 0. Are we together? Am I going too fast? Do we follow? Please let me know.
I'm following.
Please feel free to stop me and give me a ticket if I'm going too fast. I'm going, I feel like I'm going fast, but I feel also that, as you said, thank you, you are following. We are doing the math of it. I'm hoping that you got the grasp of the methodology and the approach. So now we have two equations. One is partial u and v partial a, and partial u and v partial b equals 0, right? Two equations. Then we can put them in a matrix to solve, and we can say the determinant of the coefficient matrix should be equal to 0, right? Because the two equations are equal to 0. And if we identify I to be ei0 over L square, so kind of like just make it easy, then we gonna get the equation says b squared minus, if I can read the number, 78.918 alpha p plus 61433 alpha square. That will be the determinant equation equal to 0, right? And we can solve and find p is 8,756 ei0 over L square. And this answer, you remember the other one was what? 8.902. This is more accurate because this was one term trig, and this was two terms. Right. Any questions?
Yeah, I'm confused what you did with the determinant of the coefficient matrix and the alpha. Where did you get that again?
Oh, the determinant of the matrix?
Yeah, what matrix are you
Well-
talking about?
Here is the two equation, yes?
Yeah, so you're just calling that like a 2x2 matrix?
Exactly. Solve them any way you like.
Okay.
You can solve them by elimination. You can solve them either by substitution. You can solve them. What I did, I put them in a matrix format, right? You know, I like matrices more than equation, right? So I put them in a matrix format, and the right-hand side equals 0. And I said, therefore, for the of course, the variable are. So I take the coefficient to make it to be 0, and that's what I came up with. But if you don't like what I did, you can solve these two equations any way you like. And then you're going to see, because you can see the important thing is what? The A and the A and the B and the B is canceling because they have the same power. So what you're going to be left really is those guys and those guys and those guys, which is the only unknown in this is P critical. Make sense?
Yep, thank you.
You are more than welcome. Any other
Um,
question?
Yeah, I had a question as well. Will adding more terms ever give you a less accurate result, or will it always give you a more accurate result?
No, more terms, always more accurate. This answer here, because somebody asked me in the other classes, like, is this more accurate because it's higher? Who said that? No. This is less accurate because it's always only one term trig. Every time you add a term, you're gaining more accuracy. This here is two term, and can you give me a second? As a matter of fact, I have good news and bad news. Bad news, I'm assigning you a class assignment because, and if Dylan is there, he's listening to me, please, Dylan and Martin, as we talked last night, please send the homework number, I forgot, I think number 1 or whatever, and number 2. The one who has the 3 problems about this subject, which is very much the problem we did. And that's your homework assignment. But for the same problem, here is number 7 and 8. For the same problem, practice this for me. Y is A plus BX squared plus CX to the 4 and Y equal the same problem, A plus BX squared plus CX to the 4 plus DX to the 6. For the same problem, you remember what we just did? We did the same problem using a trig by assuming delta Y one time and by assuming Y the second time. But in here, I'm assuming Y for the same problem, but I'm assuming what? Polynomial function. Which one you think is going to be more accurate? Is this one because it has an extra term? The answer for this, if you practice, will be 8.824 EI0 over L squared. The answer for this will be 8.6. Come on. Make it easy for me. 8.69. No, 8.679. 8.679 EI0 over L squared. So you see 8679, 88824. This is better than this because it has more terms. So every time you have more terms, your answer is more accurate than less terms.
Okay.
Same like finite element. When we talk about finite element, the finer the mesh or the grid, the better answer. You can have a coarse grid, you can have a fine mesh or grid. The finer, the better. Coarse, that I am more lazy than you, so I'm gonna say, okay, I'm gonna go just 4 by 4. And he said, no, I'm gonna go 100 by 100. Your answer is much better than mine. So it is always. I'm sorry?
I have a quick question, Dr. K. What does the 7-8 mean up in the top left?
Oh, problem 7 and 8.
Oh, okay, gotcha.
Yeah, I because I think what we just did 5 and 6. So those are example number. I guess it's 7 and 8. 7 and 8, and those they will take a line or two each. Or what you have to do is just here is y prime, here is y double prime, and you get to u and v, and boom, we are home, right? And the idea in here is just again to use the matrix or whatever. You can solve the unknowns anyway by even doing a matrix like what I did and find the determinant is equal to 0, or solve 2 equations to unknowns. Any questions? Because if there is no question, and now it's 6:54, so this time you are ahead by 5 minutes from the other class. I am done with what I want to tell you about the second kind of failure, which instability. We already talked about instability. We already talked about, we solved 5, 6 problems. You have the homework, you have the problem I did in the class, and also to be fair with every one of you, that somebody in the other class asked me about the quiz. The quiz on Thursday is only instability, nothing else. And the person asked about what is going to be on the exam, and if there's going to be a conceptual problem. And I said, and Dylan can hear me, I said, I didn't decide yet about, but definitely will be a problem about buckling, about instability. We'll see if I can add or not a small question about the concepts, conceptual, but nothing I didn't say in the class, nothing about the conceptual. Everything I conceptual is in the class. I said it in the class, or I talk about it, or I mention it, whatever. So but I'm waiting to see if we can add that or not. So at least will be a problem about the buckling, be critical, and maybe if there is a little bit of conceptual, one concept, if any, but maybe not. I'm not quite sure yet. Any questions? Any questions? I hope there is no questions. Let me go and see if you have any questions on the chat. Okay. The math is just tedious, not difficult. Yeah. The math is math, right? So any questions? All right. Let me go back to my page, and we will move to the new subject, which is the third element of the failure analysis. We already talked about one tension, yielding. We already talked about one compression, instability. Now we're gonna talk about dynamics. That was statics. And dynamic, and here the third subject, really what we're gonna talk about, really, is vibration. That's the, and the idea of vibration, why vibration is dangerous. If we have a governing differential equation, let's assume M, come on, M x double dot plus Cx dot plus Kx equal Fx, something like that. A mass, spring, and a dashpot. We agreed, you and I, from 331, that this side is what? I don't know what to do. Excuse me, guys, why my phone is on? Okay. The answer is yes, Dylan, you can call me. Mx double dot plus Cx dot plus, this is the system. And this is the disturbance, right? Or the force, or the load. Right? What is the problem? The natural frequency. Natural, come on. Natural frequency. If the natural frequency of the load and the natural frequency of the system are equal, it's a disaster. Why? Because the deflection of the system goes to infinity. And that's disaster. So really, the problem of vibration is we should be able to calculate the natural frequency of the system and or the force. In this case, we take the system under the load. When we know the natural frequency, we make sure that they are not to be equal. So if I'm designing a bridge, I should be able to calculate the natural frequency of the bridge. And I make sure that when the train is going by, that the train doesn't have the same natural frequency, or else the bridge will be completely destroyed. So really, to talk about this subject, I think on the syllabus, one of the references is the air. Come on. Do I need to change the page again or what? The aircraft structure for engineering students, and that's you. And the author is T.H.G. Megason. And I'm sure a good number of you knows that book because also, if I'm not mistaken, you guys have it in your design lab or class. And mainly, I am looking at chapter 8 and chapter 13. Chapter 8 is airworthiness. And maybe airframe loads. So I'll talk a little bit about airworthiness, even though that's not the subject at hand, but it's really, it comes from there. Then chapter 13, and that's more like the subject we want to talk about, is aeroelasticity. It just, that's me saying, I don't know if what I'm saying is accurate. The way I look at aeroelasticity as a branch of the airworthiness, if you know what I mean. And I will try to explain in the next hour or so we have. So these are the two chapters from the book I'm gonna refer to, because from aeroelasticity, we're gonna have static, stability again, and we're gonna have dynamic stability, and that's the vibration. So really, we're gonna start talk about vibration really as a branch of the aeroelasticity situation, whereas aeroelasticity is kind of branch of the airworthiness. So we're gonna talk about airworthiness first, then we talk about aeroelasticity, and that will take us to the vibration, and mainly we will be talking about the flutter, which is really kind of like the merging of the aerodynamics forces with elasticity forces on an elastic structure, like the wing as an example. So imagine that you take an aerofoil wing and stick it under the wind tunnel. That's a structure under aerodynamics loading. And it's gonna cause deflections, and that can lead to fraction, failure, static, stability, and or dynamic stability under vibration. Can lead to be stable or not stable. We'll discuss that. But before I go to chapter 8 and 13, let's just have a philosophical discussion. Everyone took 204 and 207 CE. Long time ago, the CE department used to call this class strength. Come on, pen, right? Strength of material. Strength. How can anybody tell me, is this title for a class accurate or not accurate? Or why, and why?
Not accurate.
Anybody? I'm sorry?
Not accurate.
Why?
Because strength of materials implies the material is failing, but mechanics of materials implies like the performance up to failure as well.
That's a very good point. One more reason.
We talk more about structures than materials.
What do you mean by that?
Like materials makes it sound like it's we're looking at purely like just elements, but we're looking at like bridges and planes, not just materials.
You're saying that you are talking about stress analysis versus material engineering kind of like.
Yeah, that's what I meant.
Okay. But let me share with you my point of view, because I really, and that's a long time ago, in a long time, maybe 20 years ago. I talked to them and I asked them to change the title to Mechanics of Material. And I think now it is Mechanics of Material, if I recall that right. Let's look at this. Come on, help me. Right? You take the specimen to the Instron machine in the lab, and you get something like this. Why are you not writing? What do we call the y-axis? Anybody remember? This is what we call the stress strain curve, right?
Strength, agility, something like that.
Thank you. Strength and ductility. And allow me today, instead of ductility, I'm gonna use another word. Anybody help me? Another word for ductility.
Compliance, strain, stiffness.
Here we go. Stiffness, which is a presentation of ductility, right? So ductility is right, nothing wrong with it. But so really the two areas in the analysis of mechanics of material is strength. Oops. No. You are doing that. All right. Okay. The strength and the stiffness. So to call the class a strength of material, you are really ignoring half of the curve. Yes, strength, there is this one here, the end of the straight line, and we call this what? Sigma P, the proportional limit. And that's the limit of linear elastic material. Linear elastic material means the end of the y equals mx plus b. Sigma is E epsilon. After sigma p, is not a straight line, but it's still elastic. So this is linear elastic, and if this is sigma yield, then this is non-linear elastic, but it's still elastic, but it's non-linear. So sigma p is the end of the linear elasticity, whereas sigma y is the end of elasticity. And the distance between p and y is the non-linear elastic. And then there is sigma ultimate, and there is sigma failure. So in the strengths, yes, there is sigma p, there is sigma y, there is sigma ultimate, there is sigma failure. All right, I have full respect for that, no problem. But that's only under the title of strength. So what goes under the title of stiffness? Like when you say stiffness matrix. Stiffness, there is in the linear, right? Elastic, and linear and non-linear, whatever, and then plastic. If we are elastic, we have E, we have G, we have Poisson's ratio, and then we have G equal E over 2, 1 plus nu. But in the plastic, which is after sigma yield, right here, you know, if this is, doesn't know why it doesn't, in here, there's plastic, and here is elastic. Then I have here the 3, but I have here the E and the G and U for elastic, and then 9 more material parameters. So there is like 12. All that is under the title of stiffness. And as a matter of fact, as I said, in theory of failure, in the yielding, we said we considered the stresses. We didn't consider the displacement. We didn't consider the stability. And of course, we didn't consider the stiffness. Now it's the time to pay more attention to the stiffness, because the subject of stiffness is very, very related, or is a very, very important part of studying aeroelasticity. And from there, very, very important part of studying the stability. And from there, it's very, very important part to study the dynamic stability. And from there, it's very important part to study the flutter. And that's the subject we need to get into by the end of today or a little bit early on Thursday, which is the flutter, which is the vibration under the combination of aerodynamic loads and structure loads on an elastic body, especially when we have some inertia force added to the situation. So now, one more point before I go into the subject. There are two different kind of I'm gonna call it just stress strain curves. I'm calling it stress strain just because I'm lazy, but you know, we mean strength and ductility and stiffness. One of them we just talk about, which is this. We call this monotonic loading. As I'm sure you did in the lab, you put the specimen and you pull it. One end is staying and the other end is pulling. That's how you get the stress strain curve as such. And we did that. Yes, there is, as I said, two curves here. One called engineering, and this called the real or natural. Of course, natural. Engineering, that's why we use factor of safety, because not 100% accurate, but that's a different story. But the other curve I'm talking about is this. Here is the stress and strain and stress. And what we do, we load and tension, then we unload. So we load and tension, and then we unload. Then we load and compression, then we unload. This here, like this, is to be considered one cycle. So this is monotonic loading at that cyclic loading. And you can go one cycle up to million, whatever. And every time you go and you come back and you close, you really don't go back to zero. You lose a little bit. And you go one more cycle and you lose more a little bit. So really, you are, every time you go to a cycle, you do not end up to the original point. So you're really moving along the x-axis, then you have a permanent deformation. What do we call that? The cyclic loading is fatigue. And that's very, 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 very bad news. And the idea is not how big is the load, but really is the delta sigma. There are two types of fatigue. Mechanical fatigue, delta sigma. Thermal fatigue, delta temperature. And as I told the other class, I think was toward the end of the Second War, this big ship, and it's on the cover of one of the fracture mechanics book. In the morning, they found it's floating in two pieces, broken into two pieces, floating apart. The ship used to be loaded with, like, say, oil tanks and sitting in the ocean. They thought that this is the work of the enemies. but later they found that's not. It's the work of fracture mechanics. In the late 40s, the fracture mechanics was not a subject. People didn't know about. I graduated from Cairo University 69. I didn't study fracture mechanics. By the time I come to the United States in 77, my doctoral degree is fracture mechanics. So the idea is they found that when they unloaded those oil tanks, say 5 on this side and 5 on this side, they didn't do it evenly. They did it, say, on all the 5 on the right side and then all the 5 on the left side, which is fine. That should be okay. Then the ship is sitting in the ocean water. That's salt. That's fine. The temperature of the ocean at night is cold, and in the morning, during the day, it's warm. That's fine. So where is the problem? There was a crack somewhere on the ship. There is a flaw, a crack. And due to the salt water, there is corrosion. Due to the change in the temperature, there is thermal fatigue, delta T. And because they unload the shipment not evenly, that's delta sigma. So between delta sigma and delta T and the corrosion, the crack kept growing and nobody is watching it till reach a critical size and the ship was broken. And that's one of the first cases of what they call fracture mechanics. And the corrosion itself can go into cycles. And delta sigma and delta T. So really, we can say 90 to 95% of fracture mechanics. And we say fracture mechanics means broken, is due to fatigue. Let me write fatigue so nobody said fat. Fatigue. And 90 of fatigue is due to stress concentration. And what do I mean by stress concentration? When you do this design, that's a stress concentration. This design is better. You have a radius of curvature. Optimum design is this. It's a zero stress concentration. So really, if you have a plate like this, an identical plate like this, but this has a notch or a crack or a flaw, this one can take 150 before it breaks. This one will break at 50 psi. So really stress concentration factor is about 3:1. And stress concentration factor cause fatigue. So bad design give us or cause, please. stress concentration. And stress concentration will give us fatigue. And fatigue will cause fracture. So fatigue is very bad situation, and if for a monotonic loading like this, and if this sigma yield is 90, due to fatigue, fracture failure is gonna happen at about 30. That's how bad fatigue is. You think you are choosing a material with sigma yield 90, your forces and stresses are good, but surprise, surprise, the structure is collapsing at 1/3 of sigma yield. Why is that? It's because of fatigue. And that's why all the airplane built in the 40s and the 50s, now they revisit them and reanalyzing them, taking fatigue into consideration. Okay, so talking about these 2 points, the idea of the mechanics material versus the strength of material and the different kind of stress strain curve. Let's start talking about, as I said, if the pen help me, that's chapter number 8, and that's the airworthiness and the airframe loading. Right? And of course, we will get to there from aeroelasticity to aeroelasticity. As I said, I look at aeroelasticity as a branch or development from the airworthiness. The airworthiness really, what is the main concern? So for aircraft and or spacecraft, right? The main concern in the airworthiness is the standard safety incorporated in all aspects of construction. And that's includes a long list, but one of them, as we said, structural strength, structural stiffness, weight, and other factor, including provision of certain safeguard in the event of crash landing, God forbid. So really that's the concern, or that's kind of like a specialist of airworthiness and really aeroelasticity concern about. Kind of like, and I don't want to get into details, it just I cover that more in details in the structural dynamic class when I used to teach it. I have 531 and 534. But anyway, then we have like something like design requirements. And you guys know this better than me. You are taking the design, and I'm sure when you design your aircraft or spacecraft, you get your design requirements. What are we talking about? As an example, as I mentioned, we worry about aerodynamics. We worry about performance. We can talk about electrical system, which I have no idea about. But people, that's why in your design you bring people from electrical engineering. And also the hydraulic system. So, you know, whatever system you have, things like that. But then also another subtitle is really the minimum standard of safety, which is take us to like what we've been talking about. We talk about factor of safety. So in here, for standard of safety, maybe what is the operational requirement? And as I said, what about the minimum safety requirement? What about recommendation practices? What you do, what you don't. What is the best practice for this situation or the other situation? And as you, I'm sure all of you do, doesn't matter which side of the alley you're on, is the space or the aircraft, is the design data, you know. So we look at all that, but let's take a look at, since this is not all our subject, but this is kind of, I thought it will help you and I to go through that introduction. Let's talk about what really get us closer to our subject. And what will get us closer to our subject, well, we're still talking about airworthiness, but the subtitle I need to discuss with you is really the structural aspects of airworthiness. What are the structure aspects? And as you and I said, we agreed that there are two structural aspects: stiffness and strength. These are the two we need to talk about. Right? Structural aspects. The strength, which is the stresses, and the stiffness. Let's talk about the strength because it's going to take us to fatigue and we will stop. We're really not concerning ourselves in this application with the strength. We already did. We took the elastic end of it, which is yielding. Fatigue will take us to the plastic end of it, which is fracture. So really, what is in here, what is the situation in here, is the magnitude of both ground and air loads. The magnitude of both the ground and air loads, especially that they are function, those loads, of selection of maneuvering and other conditions applicable to the operation or operational requirements. So really, the problem with this is the fluctuating loads, which introduce, as we said, fatigue, which introduce failure by fracture. And full stop. That's, again, as we said, this side here, strength. We already talked about half of it in the linear part. That's yielding we are not talking about the other half, which is fatigue, which is fracture. And that's usually, I talk about it in Aero 535. That's fracture mechanics class, right? Anyway, so enough of that. Let's get to the stiffness, which is really the point we need to talk about. And in the stiffness, in here, that's where we get to really the aeroelasticity. Elasticity. And that's, I said, chapter number 13 in the Magnuson book. What is the aeroelasticity? As you can see the title, aeroelasticity. As you can see, aero and elasticity, two words, two titles, two subjects. So what is aeroelasticity? It is the interaction, right, action of what? As we said, aero or aerodynamic. Let's make it, spell it out, dynamic, right? And elastic forces. That's really, by definition, is what we call aeroelasticity. And we're gonna give more explanation, but so let's really forget about the strength and let's talk about the stiffness. So we're gonna talk about aeroelasticity. And we said it is the interaction of aerodynamics and elastic forces. We said that. But there are two, what do I want to call them? Two phenomena, two scenarios, or two situation, whatever, situation. Come on, situations. One of them, as we just said, or is it, you know, and let me also write, because many books use phenomena, they are the same, really. Number one is, as we said, it is the, I'm repeating myself, action of aerodynamic and elastic forces. Okay, thank you. That's number one. We said that before. We're just repeating yourself. So what is number two? same as 1. That's why I repeated number 1. So what's the difference? But the difference is that this case number 2 with the inertia of the structure. The problem with that the inertia of the structure is a dynamic loading. Gust. And that will do what? Badly will cause oscillations. So now, under the title of aeroelasticity, we have two situations, one with and one without the oscillation force, the dynamic loading, the structure inertia. So we end up with, from here, two situations. One of them is static stability. And one of them is dynamic stability. Really, we are not concerned about static stability. We are concerned about dynamic stability. But just a minute or two. How are we doing this time? 7:50. A minute or two. Static stability. Static stability, 3 subtitles. The load distribution. Load distribution. The load distribution is static and or steady. Come on. We don't have time. Come on. Steady, static or steady state system of aerodynamic and elastic loading. So it doesn't have the inertia part. It's just, as we said, static and or steady state system of aerodynamics and structure and elasticity load. This kind of situation can lead to one of two solutions or two situations. One of them, so that leads to what? Failure for the case of extremely flexible aircraft, spacecraft structure. if we have an extremely flexible structure, it will fail. And here what's going to happen is divergence. So that's for this case. Divergence, we're going to diverge from the stability. We're going to be not stable, which is failure. When? For this case. All right. So what is the second situation? For the case of I don't have much time. Give me a second, please. Jenny, I need to call my wife to put the lights on. She's not hearing me. Can you put the lights for me on, please? Can you put the lights on? I'm sorry, guys. I'm calling my wife. The lights, please. Thank you. Love you. I'm sorry, guys. Yeah, I couldn't see what I'm writing. So for the case of, as you said, failure for the case of extremely flexible aircraft or spacecraft, that's going to be bad news because we are having divergence. But if the structure is not extremely flexible, if it's sufficiently flexible, let's say that, if the aircraft and or the spacecraft structure is sufficiently flexible, then what's going to happen, instead of divergence and we become not stable, what's going to happen, we're going to have convergence. Come on, right, man. And we reach stability, and that's in here, control reversal, which will be stability. So again, and we're not talking about that, again, in the case of static stable, we have a set of loads, the load distribution, a static and or steady state system of aerodynamics and elastic loading. It depends on the structure, extremely flexible or sufficiently flexible. Extremely flexible, divergence will take place and we'll have failure. Sufficiently flexible, it will maneuver itself and will converge itself to some kind of stability, and that will be this case, control reversal. And as I said, this is not our situation. That's again still static stability. Really what we are talking about is really here, dynamic stability. So really, we're getting closer, guys, to the subject. We are talking about the airworthiness that takes us to stiffness and strength. Strength to give us fatigue. Stiffness to give us either static equilibrium, static stability, and or dynamic stability. So we are talking about dynamic stability. And in there are again three subtitles. The dynamic response, there is buffeting, but really my subject, which is the most important one, is right here, and it is the flutter. And that's really the most important subject for what we are talking about. Why? Because this is what we call it structural vibration. I have 1 minute, but I don't want to, I don't want to keep you late. But let me write this here. What is flutter? As we said, that it is important element of the dynamic problem of aeroelasticity. And you know what? It's 8 o'clock. I'm not going to continue. I will stop right here. And I will start, God's will, on Thursday by talking a little bit more about the flutter, and then get into a little bit more about what we're going to do. But I expect maybe for the first half an hour on Thursday, I'll be still talking about the concept of the flutter and the concept of vibration. And then I will start maybe, because only we have an hour and a half, in what I need to do 2 to 3 problems, mainly about vibration. One of them is a system of springs, and the other one is a system of mass and a beam, and see how we can calculate the natural frequency for those systems. And we will be using the unit load method, if you remember that from 331, and we'll be using the eigenvalue, eigenvector concepts. Any question from anyone? Any questions? Is everybody still there? Hello? Okay. It
I think
seems
we're
like there is
good.
no question. No question.
Yeah, no
Thank you,
question.
everyone. I'm sorry, go ahead.
No question.
Oh, no questions. Okay. Thank you, everyone. Appreciate it. And I'm sorry, it's 8:02, so I'm 2 minutes over the time. Good night, everyone. Stay safe. Stay healthy. Good luck with the studying and doing the homework for the the quiz on Thursday. And remember, I have office hours tomorrow from 1 to 5 on the same link. Good night, everyone. Thank you very much. And bye-bye.
Hey, Dr. K.
Thank you, Dr. K.
Sir, thank you. Yes. Thank you very much. Appreciate it.